AP Chemistry, this is the day 50 lesson on Hess's law, enthalpy of formation, bond energies. We did a number of these problems in class, and I'm going to go ahead and do them for you here. I'm going to say in advance that you do not have to do anything on page 6 or page 7 of the assignment. You can totally skip those, all right? So let's go ahead and we're on number 11, and we're doing standard enthalpies of formation. So what you're going to need for that, okay, so what we're going to use for these are the enthalpies of formation that we came up with here. You don't need to know the equation, you just need to know what the compound is and what its enthalpy of formation is. That's how much heat it gives up when you create that compound from its basic elements in their most stable form. And it's 1 mole. It's for exactly 1 mole. All right, so let's go ahead and do this one. So what we're trying to find out the enthalpy of the reaction when we combust propane with oxygen to get CO2 and H2O. So let's go over here and just fill in the values up above here. So for propane C3H8, it's right here. It's negative 2,220. Oxygen. Oxygen is a pure element, so it has no enthalpy of formation. Carbon dioxide. 1 mole of carbon dioxide is negative 393.5. And water in liquid form, be sure you see what the state is negative 285.8. That's all in kilojoules. Okay, so always write the formula out. The enthalpy of reaction, how much heat will go into or come out of the reaction, is equal to that is the number of moles of each of the products over here, and it's the enthalpy of formation, these numbers up here, at standard conditions, and that's 25 degrees and 1 atmosphere of pressure. Okay, and then you subtract from that the same thing from the reactant side, this over here. Okay, so subtract enthalpy of formation, number of moles you have to take into account, and the delta H. Okay, so basically everything here is going to come over to this side. So let's go ahead and do that. And then you have to take everything from the reactant side and put it over here. Okay, so it's 3 moles of the enthalpy of formation of CO2 plus 4 moles enthalpy of reaction of water in liquid form. And then you subtract from that the same thing on the reactants. Of propane, it's negative 222. There's 1 mole of it. And there's 5 moles of oxygen, but it has no enthalpy of formation because it is a pure element. And at this point, it's just arithmetic. Okay, and so what we get is when we compute this for the products, we get negative 2323.7. Over here, it's just simply the negative 220. So it's minus a negative. Be careful on that. That makes it a plus. And what you end up with is the delta H of this reaction is negative 103.7. Okay, let's go on to this next one. And the last two, you're going to have to look the values up in the textbook, all right? You don't have this and you don't have this. So I mentioned that in class, but I didn't write it in the instructions here. So let's do that together. So where you go for that is Appendix C. And there it is. It's way in the back of the book. You just go way to the back of the book and just look through the appendices. Those are always in the back of any book. And you're going to find Appendix C. And it has different thermodynamic quantities. So what it's showing us here is delta H of formation. That's what we're interested in. Delta G and S are concepts we'll get to later in the class. So the two that we need are C2H5OH. And you find that under carbon. It's a little hard to see, so I'll try to come out a little bit here. And that one is right here. it's C2H5OH liquid. We're going to use the liquid form here. Is negative 277. Negative 277.7. So I'm going to write that down. So that's this one right here. Kilojoules. Now let's come down to problem 13. Let's look it up while we're in the book right now. HBr. So HBr is right here. It's under bromine, not under hydrogen. There it is, HBr as a gas. And it's negative 36.23. So that's where you would get those. So that's how you would use this appendix in this book. Okay, so we'll do that one next. Let's go ahead and take care of this problem up here. So for O2 we have 0. CO2, we've done that one before. Come over here, CO2 is negative 393.5. And H2O, it's in liquid form also, and that's negative 285.8. Okay, so you're going to compute this the same way you did the last one. The delta H, the change in enthalpy or change in heat of the reaction. Okay, so it's the heat of formation of the products. You always have to multiply that heat of formation times the number of moles of each product, and then you add them up. Do the same thing over with the reactant. So the products are over here on the right, so we're going to bring these over here. Okay, so it's 2 times this number, 3 times this number. Then you're going to subtract. That's why it's good to use square brackets here, because the negative sign is going to carry through. And you come over here. Okay, enthalpy of formation for this compound and enthalpy of formation for O2 is 0. Alright, so now it's just arithmetic. Go ahead and do that. I first do these, then I do this, and then you're going to subtract those. Okay, and we're back, and I went ahead and did this calculation. I got that. I did this calculation. I get that. Be careful of the double negative sign, so you're going to end up adding 277 to this. And when you do that, you end up with the heat of reaction is 1,366. So what does that mean? Be sure you can explain in words. That means when you do this chemical reaction, this much energy, and I should have units of measure always, this much energy in kilojoules in the form of heat, it's heat energy, will come out of the reaction. It's exothermic. The negative sign means the heat's coming out, just like your bank account, money coming out of your bank account. All right, there you go. So let's do the last one here. So we went back to Appendix C and we found out what the enthalpy of formation for HBr is, hydrobromic acid. All right, so let's go ahead and write the equation. This is required. I want you to write the equation every time. Then it ends up committed to memory. It just takes 30 seconds or so to do it. Okay, products, reactants. Products on this side, reactants on this side. Okay, let's go ahead above each of them and put in what the enthalpy of formation is. We already have it for HBr. For oxygen, it's 0. For water in liquid form, that's what we've been doing the whole time here, so it's negative 285.8. And bromine, Br2, is in its natural form. It's a diatomic molecule, so it is what it is. It has 0. It is an element. It's a pure element in its most stable form. So you've got a couple of zeros there. That makes the problem easier. So go ahead and plug in the numbers. So again, when you do this reaction, negative 426, you don't have to say negative, 426 kilojoules of energy will be released by this, will go out of this reaction. By saying going out of the reaction, you're saying that it's negative. That's negative enthalpy. All right, so that takes care of our standard enthalpies of formation. They're pretty easy. The hardest part is doing the arithmetic without making a mistake. Okay, now we're going to move on to Hess's law, and we're going to do about 3 or 4 problems of this. Do not do pages 6 or 7. Those are completely wiped out, so you don't do any of those. So Hess's law is basically a situation where you're trying to find the unknown enthalpy of a chemical reaction. So this is the target reaction. And what you're going to do is you're going to use 2 reactions of known enthalpy. So you know the enthalpy. So you're going to do kind of almost an algebraic manipulation of these 2 to create that reaction. Okay, and the rules are simply you can flip the reaction or reverse it, switch sides. So the CO goes to this side, the C and the 1/2 O2 go to that side. Let's use this as our example. So the CO2 goes to this side, C and O2 go to the right. If you do that, you change the sign on the enthalpy, okay? So for reversing the reaction, you change the sign. The other thing you can do is you can multiply through by a factor. Just like distributing a number in an algebraic equation. You can multiply this by 2, this by 2, this by 2. What that does is it multiplies the enthalpy by 2. So if you multiply the reaction, then you multiply the enthalpy. Let me just call it delta H. Okay, and finally you can add and subtract. And you do this at the end of the problem. So you can add on the same side. So I could add, for example, carbon dioxide there, and have 2 carbon dioxides. So you add if they're on the same side of the arrow. And you subtract if they're on opposite sides of the arrow. Again, you don't do that until the very end of the problem. And those 2 kind of go together there. So those are the only 3 things you can do. So those you play around with, and it's like a little puzzle. All right, so what you do is you look for an element that only appears once. So stay away from oxygen because it appears in both of these reactions. So you want to save that for last. But you see that carbon here appears, in the target reaction, it appears on the left-hand side of the arrow. I like to circle the arrows to be clear which side of the arrow I'm on. It's on the left-hand side of the arrow, and there's 1 mole of it. In this reaction, I have carbon on the left-hand side of the arrow, and there's 1 mole of it. That means I don't want to change anything about this reaction. Carbon is already what it should be and where it should be, so we're going to leave that one alone. I'm going to number the reactions 1 and 2, and then I'm going to come down and rewrite them as I make changes. So this is going to be 1A, and it's going to simply be this reaction that I haven't changed. And I'm going to omit the states. They're not significant in doing a Hess's law problem, but you should really put them in. All right, I'm just going to try to save a little time here. Okay, and that means the change in enthalpy is the same as it was originally right here. Okay, so now that I've written that, I'm going to lightly put a line through this so I don't accidentally add it in a second time there. Now, we come down here. We have CO. If we look at our target, we have CO. There's 1 mole of it, and it's on the right-hand side of the arrow. It's off to the right of the arrow. Here I have 1 mole of CO in equation 2, but it's on the left-hand side of its arrow. So what we're going to do is reverse this. We're going to turn this around so that the CO goes over to the right side, so it will be where it should be there. So we're going to come down here. Okay. And that's what you... Let's see. Did I do that? Yes. That's what you get. Okay. So I turn this equation around. What that means is when you reverse the equation, it says you change the sign. So I take this number and change the sign. So it's delta H equals positive 283 kilojoules. Okay, now let's see if everything adds up properly. So I look, I have C right here and it's nowhere else, so it's going to come down here. It doesn't cancel. What else do I have? I have CO right here on the right hand side of its arrow. And I like to circle the arrows. The reason I do the circle of the arrows is because the arrows don't always line up. So you could get confused as CO, you can look at that arrow, it looks like it's on the left, but no, it's of its own arrow. Okay? So the CO is on the right, so it's over here. And it's on the right hand side of the arrow. So I'm just going to lightly cross out those two because I've used them. Now you have CO here on the right hand side of this arrow and over here on the left hand side of this arrow. That means you're going to subtract those. Now you're ready to do the adds and subtracts. So these two are basically going to, CO2 minus CO2 goes to nothing. It cancels out effectively. And now finally you have an O2. You have one O2 on the left hand side of this arrow and you have a half of O2 on the right hand side of this arrow. So what you do is subtract because they're on opposite sides. So 1 O2 minus 1 half O2 gives you 1 half. 1 minus 1 half gives you 1. Gives you 1 half, excuse me. Now which side does it go on? Well, it goes on the side that had the larger of the numbers. 1 is larger than a half, so 1 minus a half is going to give you 1 half over here. Okay, and we use those so they can scratch those, so we check. And this is our target equation. It's what we were shooting for up here. So now that we know, the reason you do all this is to be sure you actually did arrive at your target. Once you do that, this is really what you're interested in, is this addition over here. Okay, and when you do that, negative 395.5 plus 283.0, and that's going to give you the delta H of the reaction, which equals negative 110.5 kilojoules. Okay, so when you perform this reaction, 110.5 kilojoules of energy will be released. It's negative. It's exothermic. It will exit the reaction into the surroundings or the atmosphere. Okay, not so bad, is it? Let's do this one. This one's easier. Now, in this case, you have carbon and carbon, but you have them in different forms. So you're going to treat them like different compounds. Carbon diamond and carbon graphite. So you're not going to be able to cancel carbon and carbon when you get down into doing the problem here. Okay, so very simply, let's number our equations. And let's see. So let's see carbon diamond. Let's take that. It's on the left-hand side of its arrow. There's 1 mole of it. In equation 2, carbon diamond is on the left-hand side of the arrow, 1 mole, so we don't want to change carbon diamond, okay? We want to leave that the same. Leave that reaction the same. Carbon graphite appears on the right-hand side of the arrow in our target. But up here it's on the left-hand side, so we're going to have to reverse this. So let's come on down here and do that. That's equation 1A. Okay, and what that means is we're going to have to take this and change the sign on it. Okay, there you go. And then we said number 2, the diamond, we were going to leave it alone. But let's rewrite it. You say, why do you have to rewrite it? It's already there. Well, because you might do several iterations, several steps down on some of these problems. But these are fairly simple. But I still want to just develop some good habits here. So I'm going to write it down here. Okay, and since we didn't change this equation, you still have the same delta H. Okay, so let's see if our reaction works here. We have carbon graphite on the right side of the arrow. And we have carbon diamond on the left side of its arrow. All right, up here we have CO2 on the left side of the arrow here. And down here, it's on the right side of the arrow here. So now we're ready to start doing add, subtract, in other words. So CO2 minus CO2 cancels out. and then you have O2 right here on the right side of its arrow, and here this O2 is on the left side of its arrow. Again, that's why I like to circle the arrows, because they're not lined up. O2 is on the left side of its arrow, so these two cancel out. And so all you had left was the diamond and the graphite. So now you're ready to go ahead and get your delta H of reaction. And the reaction is simply carbon diamond degenerating down into graphite. Okay, it's just reducing down because this is more stable form than this, even though diamond is the hardest substance on Earth. And the enthalpy will somewhat show that to you. So if you take the 393.5 and subtract the 395.4, and you get 1.9, negative 1.9. So that's negative 1.9 kilojoules. So it's at lower energy. Generally, lower energy means more stable when it's in graphite form. Okay? All right, there you go for that. Okay, so we move on to number 16. This is our target. And we're trying to recreate that by these two. All right, so I'm gonna label them 1 and 2. And I look at this. Okay, so number 1. Well, first of all, let's pick an element to start with. Stay away from oxygen because it appears in both equations. Let's go with P406 or P406. Yeah, it appears only one time, and it's right here. Now, in equation number 1, it's on the right-hand side of the equation, but in our target, it's on the left. So we're going to have to reverse this equation. Okay, so we reversed this equation right here, so we had to change this to a positive 1640. Okay, P4010 is on the right side of the target, and in equation number 2, it's on the right side as well. And it's the same number of moles, and I should have pointed it out for P406, same number of moles, so you didn't have to multiply by anything. So that means we're going to leave equation number 2 alone. And I go ahead and write it, because I just want to show you good form. Not all the problems you're going to see doing this are this easy. So we're going to go ahead and write number 2. Okay, you didn't change this, so you don't change the enthalpy of that. Okay, let's go ahead and put them together now. All right, so P406 only appears once, and it's on the left side of the arrow. Again, circle your arrows, again, because they're not lined up, it can be confusing. So P406 appears on that side. Okay, and then let's see, on the right side I have P4010, and that doesn't appear anywhere else, so that's going to be over here. Okay, and finally you have, so we've taken care, I'll just lightly cross them out because we've dealt with them already. Okay, now on this side you have a P4 on the left side of the arrow, and you have a P4 on the right side of this arrow, so those are going to subtract, so they basically cancel out. And now what you have is you have a 502 on the left side of this arrow, and you have a 302 on the right side of this arrow, so that's going to be a subtraction. So 5 minus 3 is 2, and it goes on the side of the bigger of the two numbers, the 5, so it's going to be plus 202. Okay, and if you look up here, that is your target. You got your target. So the reason you do this is to verify that you have got the target set up, so that means the changes you made over here, this is really what we're interested in, are going to be correct. Okay, so now we can go ahead and add these two numbers, and that gives us 1,300 for the delta H, or negative 1,300 for the delta H of reaction. Again, exothermic means energy is coming out of it. Okay, so negative, let me get that clear. That's kilojoules. That much energy came out in the form of heat. Okay, there it is. All right. Keep going. And 6, we're going to scratch. We did it in class. There's an issue about those oxygens there. I've had an explanation. I've had another colleague tell me that's not a legitimate reaction for this mechanism, so we're going to skip this one, okay? We did it. We kind of fudged it a little, but at least you learned the process in class, but we're not going to do it here. Number 6, I meant to take, or excuse me, page 7, I meant to take out, and I didn't. That wasn't even supposed to be there, so scratch that. Don't worry, you'll get plenty of other chances to practice this. So now we're going on to page 8, and we're moving on to bond energies. All right, so bond energies is an approximation method because you're using average bond energies of a certain type, like HH bonds. Not all of them have that much energy. This is the amount of energy in an HH, a hydrogen-hydrogen single bond. It's that, but it's average. There are some that have considerably more than that, some that have considerably less than that. So you're using an approximation method here, but it's something that you could be asked on the AP exam. Okay, so you'll need this table to do this problem, and this is really just a lot of arithmetic here, okay? So we will do this here. So what you're saying is you're going to count literally how many of these types of bonds you have, of each type of bond, and assign to it this number. So what we do is for CH4, we have 4 carbon-hydrogen bonds. 1, 2, 3, 4. And there's one CH4. This is a balanced equation. So there's one CH4 molecule. So what I'm going to do first is write the number of molecules here is 1. And then I'm going to write down the number of bonds per molecule. CH4. And let's write what type of bond it is. So CH. Right there. Okay, and I've got 1, 2, 3, 4. And now I have to go up to the table here, and a CH bond is right there. A CH single bond is right there. It's 414 kilojoules per mole. Everything is going to be a positive number until you get to the very end in this type of problem, okay? So let's go ahead and set up all the equations, and then we'll go ahead and just do the arithmetic to solve the problem. Okay, so here you have an oxygen molecule, diatomic oxygen molecule, which has a double bond. So, and you have 2 of them. So if you wanted, you could draw a second one, but not really necessary. Let's do it just for this one problem. I'm just going to draw a second one so we can actually count. Okay, there you go. So you have 2 of them. That's what this says, 2. So we have 2 of those. And in each one, there is a single oxygen-oxygen double bond. So there's 1 in each of those. And then what's the energy in that? You got to come up here and find oxygen-oxygen. There it is right there, oxygen-oxygen double bond. Now, what the red means, you can just read the note. Bond energies in red are for diatomic molecules, not an average. So this is actually the exact energy. This is a diatomic oxygen molecule, so that's the exact energy that it has. That's all it's saying for that. So it's 498.7. Okay, and we're done with that. Let me draw a little light line right here. Now we go to CO2. We have 1 mole of that. So we have, or one mole or 1 molecule, either way you want to say it. So there's 1 of those. Now how many bonds? Well, each one has a carbon-oxygen double bond and another carbon-oxygen double bond. So you have 2 carbon-oxygen double bonds. And we come up here to find that. And carbon-oxygen. Now it's a little tricky here. You got carbon-oxygen single bond. You don't want that. It's a double bond. But you have 2 that are carbon-oxygen double bonds. So which one should you use? Well, if you read the note, the bond energy from CO. So that's a very specific bond, is carbon-oxygen, is this one. But that's not what we're dealing with. We're dealing with CO2. So it's going to be the 745. That's the average for a CO bond. Okay, again, this is specifically, it says down at the bottom, for NO, or excuse me, for CO. And we're not dealing with CO. We're dealing with CO2. Okay, so 745 is going to be this. Energy. Finally, we have 2 water molecules. So let's go ahead, and you don't have to draw the number that you actually have, but we'll do it for this first problem. So we have 2 molecules of water. So let me draw a line there. 2 molecules of water. And each one has 2 hydrogen-oxygen single bonds. And the energy in a hydrogen-oxygen bond, it doesn't matter whether you call it OH or HO, it's the same thing. It's a hydrogen-oxygen bond, is 460. All right, and that's all the equations that are set up. So now what I'm going to do is I'm going to do the math this one time, because you want to be careful on the math on these problems. It's sometimes the trickiest part. So first of all, you're just going to do that. And that's going to be 1,656. Okay. Now, one thing, let's actually stop back and talk about a principle here that's really critical to this whole problem. When you're breaking bonds, you're putting energy in. When you break your pencil, you have to put energy into it to break it. So breaking bonds, and that's on the reactant side. Okay, that's over on this side. Breaking bonds means you're putting energy in to break the bonds. That's going to be a positive delta H. Okay, over here, you're taking those broken bonds, those individual atoms that were broken apart, and you're putting them back together again to create a new compound. The reason they're forming like that is because they can go to a lower energy state. So what you're doing is you're putting the atoms back together. They're going to lower energy, which means they're releasing energy. Something's going to lower energy, it has to be giving off energy in order to do that. So forming bonds, okay, so that's going to be negative delta H, because as the bonds are formed, the atoms go to lower energy state and they give off energy. That means in between these two sides right here is going to be a negative sign. It's a minus, okay? These are all going to be negatives and these are all going to be positives. Okay, so let's go ahead then and finish doing our math here. Over here we have this one, and that's going to be 1490. I'm writing it as a positive number, but this negative sign is outside the bracket, so it's really a negative number as we said. So that's negative 1490. And 4 times 460 is going to be 1840. Okay. So again, we can further reduce our math. These two should be added together also. Okay. So let's go ahead and finish up the math. Okay, and that gives us negative 676. Okay, and so that's our enthalpy of reaction for this combustion. And since it's 1 mole, you can say that 676.6 kilojoules of energy are given off when you react 1 mole of methane there. Okay? All right, let's move on to 2A, and this is a hydrocarbon called ethane. And so we're going to do the same thing. We're going to combust it, but you're not going to draw all the molecules this time. You're just going to do the math on it, okay? So here it's saying that we have, here we're doing CH bonds first. Okay? So we have 2 molecules of this. And each one has 1, 2, 3, 4, 5, 6 CH bonds. Alright, so now we have to go over and see what is the energy of a CH bond. We've already done it. It's right there. It's 414. Okay, now we also have carbon-carbon bonds here. See that right there? That's a carbon-carbon bond. So again, we have 2 molecules of this, or 2 moles, however you want to think of it, and each one has 1 carbon-carbon bond. And now we want to come up and see what's a carbon-carbon. It's right there. It's 347. It's a single bond. Be careful, because you also have double and triple bonds. This is a single bond, so it's 347. All right, so let's go ahead and set up all the equations first. So we've taken care of ethane right there. Now we have oxygen. It has each oxygen molecule has a double bond, oxygen-oxygen. So, and we have 7 molecules. So we're going to come over here and say 7 times, and then the energy in an oxygen-oxygen double bond is this right there, 498.7. Again, that's exactly the energy for oxygen-oxygen, not just an average. So it's 498.7. Okay, now we come over here, and we have 4 molecules right there, and each molecule has 2 carbon-oxygen double bonds. There's a carbon-oxygen double bond, and there's a carbon-oxygen double bond. So 4 molecules, each one has 2 of those, and then we go look at the energy for carbon-oxygen double bonds. We did that one before. It's not the 799, it is the 745 right there. Finally, over here, we have 6 water molecules, and each one has 1, 2 HO bonds. And we've done this one before. We come right there. There's the HO. Hydrogen-oxygen bond is 460. It's really important to keep your work organized on this because the arithmetic can kill you here. Okay, so let's go ahead and figure out what this is. So we're going to multiply these, and then we're going to add it to this plus this. Okay, multiply these, multiply this, and then add this. And that gives us 5,662. Okay, and that's kilojoules that are going in, kilojoules that are in the bonds of 2 of these, 2 moles of ethane. Okay, come over here and you just have that single calculation there. Okay, that's kilojoules going in to break all these bonds here. These are both going into, and you're going to add those. Okay, now we're going to draw a little line right here, and we're going to do this one. That's going to give us 5960. And then finally the water. And that's going to give us, let me get that right, 5,520. Okay, and you're going to add those 2 together. But it's going to be energy in, which is positive, and this is energy out, which is negative. So I'm going to put a minus sign there and put a bracket around that. But basically the negative sign distributes all the way through to there. Okay, and now we're just continuing to do arithmetic here. Okay, and after having done all these calculations, for this you get that number, it's positive. For this, you get this number, it's minus this number. So you're going to end up with, it should be a negative sign there, negative 2327.1 kilojoules of energy will be released. The negative sign means it's coming out of the reaction. Okay, one more and we're, I think, done with this. Alright, so C3H8, again, that is propane. Alright, so here we go on this one. You only have one, first of all, you have to balance the equation. Okay, so let me write that up here, balance. If you don't balance it, you got to go back and do that. Alright, so what do we balance this to? Well, the hydrogens, they're 8, so we can put a 4 here. That'll give us 8. That now gives us, well, let's do it properly. C, H, I like to just do these in my head sometimes, but don't do it that way. 3, and over here you have 1. Hydrogen, here you have 8. Here you have 2. Oxygen, here you have 2. Here you have 3. H2O, that's an O actually. And here you have 3. Okay, we can go ahead and do the hydrogen first. So 4, that makes this 8. Alright, and now it makes the oxygens. I added 4 more, and I had 2 already, and 4 more. So that's going to give me 6. All right, and carbon. Well, if we balance the carbon now, put a 3 there. That becomes a 3. So carbon is in balance. Hydrogen is in balance. When we did that, though, we had to change the O's on this side. So now we have 3 times 2 is 6. And 4 times 1 is 4. So let's go ahead and change this to a... So that makes it 10. Again, 3 times 2 is 6. And 4 times 1 is 4. That makes this 10. Whoops, I put the 10 on the wrong side. So I still have that 2 there. Let's leave that there. So this scratches and becomes 10. Okay, so I have 10 on this side, 2 on this side. That means if I can multiply this by 5, I will have 10. Okay, so everything's in balance. So it's 1, 5, 3, 4, and I'll erase the temporaries up here. Okay, I just want to double check it. 3 carbons, 8 hydrogens, and 10, 3, 2, yeah, okay. So here we go. So we're going to have one of these. So for the CH bonds here, you have 1, 2, 3, 4, 5, 6, 7, 8. And that's going to be, there's one molecule. Let's start with that. There's 8 bonds per molecule of CH. And that's going to be, we've done this one before, it's 414. Okay, so we're all done. Well, we're not done with that. Then we have the carbon-carbon. And there's one molecule again. And there's 1, 2 carbon-carbon bonds. There's a carbon-carbon bond, and there's a carbon-carbon bond. It's not how many carbons, it's how many bonds between the carbons. So that's going to be 2 times. And again, we go back to our sheet here. Carbon-carbon single bond is 347. Okay, we're done with that. Now we go to oxygen. We have 5 molecules of oxygen. And it's an oxygen-oxygen double bond. So we've seen that several times. It's right there, 498.7. Okay, that's taken care of. Now we're crossing the arrow here. So we have carbon dioxide. We have 3 molecules of that. Each carbon dioxide has a carbon-oxygen double bond. There's 1 there. There's 2 there. So there's 2 per molecule. And we found that that is the 745 that we've used before, right there. Okay, that's taken care of. And finally, water. We have 4 molecules. Each molecule has a hydrogen-oxygen, 2 hydrogen-oxygen bonds, single bonds. So that's 2 per molecule. And that number, again, is 460 rather. Yeah, 460. Okay, so go ahead, do the arithmetic. You're going to have to add those together. So put a plus sign right there. You're going to have to add those together. And then this one is just multiply that. This one is just multiply that. And this one is just multiply that. Okay? So go ahead and do that. Okay, so where we are is you combine all of this, you multiply that, and then add them together, and that gives you this many kilojoules in those bonds of one of those. Come over here, same thing, multiply that, that's what you get. Over here, multiply that, you get that. Over here, multiply that, you get that. Okay, this is energy going out, it's negative, so you put it all in a big square bracket and put a minus sign in front, it's subtraction. And then you just do the arithmetic on this. This to this, subtract that, and you get negative 1,650 kilojoules. Okay, so I believe I've done every single problem on this assignment, either on this video or on the previous video. If I didn't do one, you're still responsible for doing it. Again, eliminate page 6 and page 7. You're not doing anything on page 6 or page 7, so that shortened the assignment. Okay, so go ahead and do this by Monday, and you want to get it uploaded. I'm available for tutoring this weekend. If you want to just email me, I'd be happy to jump on a Zoom meeting with you, and we could do a tutoring session. Just let me know. Okay, that's it, and have a nice rest of the weekend. Stay dry.